Okay, so we have seen the addition theorem of probability for two non-mutually exclusive events. And this is the addition theorem of probability for two events A and B which are not necessarily mutually exclusive. And how we write? We write PA union B equals to PA plus PB minus PA intersection B. And PA union B means probability of occurrence of at least one of the events A and B. By at least one of the events, we mean occurrence of either A or B or both of them together. So this is a derivation. It's very simple. We have derived PA plus PB minus PA intersection B. Now see, if A and B are mutually exclusive, then A intersection B will be phi. In the Venn diagram, they will not have any common area. So, and ultimately probability of phi equals to 0. And ultimately we get PA union B equals to PA plus PB. One thing you remember, whenever we use the set theoretic approach, we use the term mutually disjoint. And in classical approach, we use the term mutually exclusive. Now, for three events and A, B and C, how we write PA union B union C? You see PA plus PB plus PC minus PA intersection B minus PB intersection C minus PC intersection B plus PA intersection B intersection C. The derivation is very simple. It's very simple. Just we write A union B union C. Now B union C, we take it as a single event. For example, PA1 union A2, and then we use this expansion. And again, PB union C, we use again this expansion. And here you see A intersection B union C. This is the distributive property of the set. By distributive property, we write A intersection B union C equals to A intersection B union A intersection C. You can draw a Venn diagram and verify this. It's very simple. That means for three events A1, A2 and A3, I can write PA A1 union A2 union A3 equals to P of A1 plus P of A2 plus P of A3 minus P of A1 intersection A2 minus P A1 intersection A3 minus P A2 intersection A3 plus P A1 intersection A2 intersection A3. You see, the sign actually changes from plus to minus. How? Actually, for a single event, whenever we consider the single event, we have the positive sign. And then for compound event, I mean for two events, compound event for two events, we have the negative sign. Again, for three events, we have the positive sign. Now, I can use the symbol summation P of AI goes from 1 to 3, this much I have written. Then, you see, double summation PAI intersection HJ. And here I have written I less than J. I have written I less than J. And I greater than equal to 1 and J less than equal to 3. You see, I less than J. That means A1 intersection A2. Here 1 less than 2. Then I write A1 intersection A3. Here again 1 less than 3. Then A2 intersection A3. 2 less than 3. So, all these three terms I have written with this double summation PAI intersection AJ. Then I have written this plus PA1 intersection A2 intersection A3, and I have written plus minus 1 raised to the power 3 minus 1. Actually, my motive is to generalize this theorem for n events. So minus 1 raised to the power 3 minus 1, that means it's a positive plus sign plus 1. Now for 4 events, how can I write? For 4 events A1, A2, A3 and A4, how can I write? First of all, I write PA1 plus PA2 plus PA3 plus PA4. Then minus. For compound event, considering 2 events, I use the minus. Then again for 3 events plus, then again for minus. You see, and I write summation P of AI minus here double summation AI intersection HJ. And I less than J. That means first I write A1, A2, then A1, A3, then A1, A4, then A2, A3, A3, A4. Everywhere you see I less than j, I less than j, and I greater than equal to 1 and j less than equal to 4. Similarly, I use triple summation this, and here I write plus minus 1 raised to the power 4 minus 1. Similarly, I can write the theorem. I can express PA1 union A2 union A3 union A4 union A5 in this way. So for n events A1, A2 up to An, not necessarily mutually exclusive. How can I write? P of, you see, writing union I goes from 1 to n Ai. What does it mean? P of A1 union A2 union A3 in this way union An. Okay, so PA union AI equals to, you see, summation P of AI, then minus double summation, then plus triple summation in this way up to plus minus 1 raised to the power n minus 1 P of A1 intersection A2 intersection n. Now we use the mathematical induction to prove this theorem. For two events we have already proved, we know this for two events. So for two events that's true. That means I can write summation P of AI, I goes from 1 to 2 plus minus 1 raised to the power 2 minus 1 P of A1 intersection A2. That's proved for two events. Now I suppose that the theorem holds for n equals to r. That means P of union I goes from 1 to r AI equals to this one, summation I goes from 1 to r minus I less than j less than equal to r greater than equal to 1 in this way up to plus minus 1 raised to the power r minus 1 this one. I can write because I have assumed that the theorem holds for n equals to r. Now what happens? Let us see for n equals to r plus 1. Now see, P of union I goes from 1 to r plus 1 AI equals to this much. I can write this way. Union I goes from 1 to r AI, again union A of r plus 1. That means up to r, A1 union A2 up to in this way union AR, I have taken in one bracket union the last one AR plus 1. Now you see, if I take this quantity, that means union I goes from 1 to r AI. Suppose I take this as A1 and this as A2, and I apply this theorem for two events. So what can I write? P of this plus P of this minus P of this intersection this. Now P of union I goes from 1 to r AI, I keep it as this, plus P of AR plus 1 minus, you see, this is again the distributive property or distributive law of set theory. You see, A1 union A2 intersection A3. We just draw a Venn diagram and see what happens. This is nothing but A1 intersection A3 union A2 intersection A3. We just draw a Venn diagram, A1, A2 and A3, and all of them will have some common region because the events are non-mutually disjoint, not mutually disjoint. So you see A1 union A2, first of all you take the region A1 union A2 and then take intersection with A3. You will see this is nothing but A1 intersection A3 union A2 intersection A3. And how can I write? I can write this way. Union I goes from 1 to 2 AI intersection A3. That means for I equals to 1 I get A1 intersection A3, then union I equals to 2 A2 intersection A3. And this I have applied here. This is, for example, entire one is A1 and this is sorry, this is, you see, A1 union A2 union A3 union AR and then intersection AR. So I can write this here. AI intersection AR, I goes from 1 to R. Summation P of AI, because already I have assumed that the theorem holds for n equals to R. So I write this much expansion and then plus P of AR plus 1 minus P of this as it is. Now here what you can see, P of AI goes from 1 to R plus P of AR plus 1. These two I have taken in single summation and I write I goes from 1 to R plus 1 P of AI minus P of AI intersection AJ as it is plus on minus 1 raised to the power R minus 1 PA1 intersection A2 up to AR. This much this is, and what remains? This one. Now here again I apply the addition theorem. This one union addition theorem, union P of union I goes from 1 to R AI. Now suppose here P of union I goes from 1 to R, here AI intersection AR. I take it suppose this is a single event. How can I write this? I can write this here, summation I goes from 1 to R P of this minus double summation plus in this here minus 1 raised to the power R minus 1. Just I have applied this one because I already assumed that the theorem holds for n equals to R. That means union I goes from 1 to R AI intersection AR plus 1 equals to, I can write this way. Now you see next it's okay, this one, these terms, and I take this term P double summation PI intersection AJ plus this one in a bracket and then up to minus 1 raised to the power R minus 1. Actually here minus 1 raised to the power R minus 1 is there, and just a second. Okay, so here minus is there, minus, that means minus 1 is there, and here the coefficient is minus 1 raised to the power R minus 1. So ultimately if we withdraw this bracket, if we remove this bracket, if we take this outside the bracket, I get minus 1 raised to the power R. I tell you again, here minus 1 is there and here the coefficient minus 1 raised to the power R minus 1. So ultimately I get minus 1 raised to the power R. So that's proved. So we see that the theorem holds for n equals to R plus 1. So by applying the principle of mathematical induction, we can say that the theorem holds for all integral values of n. It's very important.